Okay, so let's consider a little bit more complicated example. Yes, so the reaction of the copper with the nitric acid, we obtain copper nitrate, nitrogen oxide, and of course water particle. And please, once again, I would like to, of course, tell you that the reaction proceeds from left to right. Yes, so on the left we have substrates, and on the right we have products. Okay, so we need to find elements that change their oxidation states. So let's make it firstly with the copper. Yes, with the copper. Okay, we could see that here the copper oxidation state, it's a metallic state, is equal to 0. Okay, and it's 0. Okay, in the products we also have a copper. Yes, and here in this salt, copper nitrate, copper oxidation state is equal to plus 2. Plus 2. Okay, so we find the element, we found the atom that undergoes oxidation reaction. Okay, so now we need to find what is reduced here. Let's check firstly hydrogen atom. Let's check hydrogen atom. On the left side, hydrogen atom is in the particle of nitric acid. In this acid, hydrogen atom is on the oxidation state equal to plus 1. Okay. In the products, in the side of the products, hydrogen atoms are in the water particle here. In the water particle, every single hydrogen atom oxidation state is equal to plus 1. So we see that there is no oxidation state change between substrates and products in the case of hydrogen atom, hydrogen cation. Okay, another one. Let's see nitrogen. Let's see nitrogen. We have a nitrogen in the nitric acid, and we also have a nitrogen in a nitrogen oxide here. Okay, so let's check it. Okay, in nitric acid, we could calculate the nitrogen oxidation state. We have a nitric acid. In nitric acid, of course, oxygen oxidation state is equal to minus 2. We have three the same atoms of oxygen, so the total given oxidation state from oxygen give us minus 6, because minus 2 times 3 give us minus 6. Hydrogen in nitric acid, of course, plus 1. So plus 1 minus 6 is equal to minus 5. It's neutral particle, so the net charge, net oxidation state of this particle should be equal to 0. Therefore, nitrogen oxidation state is equal to plus 5, nothing else. Okay, so here we have a plus 5. Okay, plus 5. So, that's plus 5 oxidation state of nitrogen. Okay, let's look at this nitrogen oxide, nitrogen dioxide. Okay, in nitrogen dioxide, oxygen atom oxidation state equal to minus 2, which in the sum give us minus 4 because we have two atoms of oxygen. Okay, the net charge of this particle of nitrogen dioxide of course, is equal to 0. So the oxidation state of nitrogen in this particle should be equal to plus 4. So we now see that there is a change of oxidation state between nitrogen in nitric acid and nitrogen in nitrogen dioxide. So there is a change of oxidation state. So we found reduction reaction. Yes, we found reduction reaction. Okay, so the oxidation state of nitrogen decreased from plus 5 to plus 4 to plus 4. Okay, let's check it for sure that there is no change, because it could be that there is no change of the oxidation state of oxygen. Here we have an oxygen in nitric acid. Oxidation state of every single atom of this oxygen is equal to -2. Here in the salt we have also oxygen atoms with oxidation state equal to -2. In nitrogen dioxide also, and in water particle also. Okay, so there is no change of oxidation of oxygen atoms. So we found two species that change their oxidation state: copper and nitrogen. Copper is oxidized, nitrogen is reduced. Okay, and on the basis of this example, I would like to show you two methods that we can use to fill the coefficients of these reactions. The two methods that we can use to fill the coefficients of this electrochemical reaction to balance the stoichiometry. Okay, so the first one, I believe the fastest one, yes? So the first one, we need to use only atoms. This method concerns the using of only atoms, not ions, not cations, not anions, not the whole particles, but just single simple atoms that change their oxidation state. So let's check it. Let's start from the oxidation reaction. We have metallic copper, which is oxidized to the copper with the oxidation state +2. Okay. And of course, we obtain also two electrons, which are removed from the atom of the metallic copper. Yes, so we obtain the copper atom with the oxidation state +2. Here, in this method, we do not write cations and anions. We only use oxidation states. So I write it in this form, not the 2 plus Arabic letter. So let's look at once again on this example. Yes, from 0 to 2 plus, but 2 plus oxidation state. It's not an ion. We do not treat as an ion. Okay, so in the reduction reaction, we need to check nitrogen atom with the oxidation state as we calculate +5. And this nitrogen nitrogen atom undergoes reduction reaction. Yes, he gained one electron and we obtain nitrogen with the oxidation state equal to 4 plus. Okay, so we have to balance the number of electrons. One atom of copper releases 2 electrons, so we need 2, we need to multiply the reduction reaction by 2 to balance the number of electrons. As I said previously, these electrons should be consumed. There is no other situation that these electrons will become free electrons. It is impossible. They need to be consumed here. However, one atom of this nitrogen needs one electron, so it should be two atoms of nitrogen. Yes, so the reduction reaction will become to look like that. Okay, so we have two atoms of nitrogen and two electrons. Okay, so here we have these two half cell reactions: oxidation reaction and reduction reaction. What else? What's more important here? I told you that in this method we do not use ions. We are writing this the so-called ions here as atoms with oxidation states in the superscript oxidation state here. However, we need to remember that we must also make here balance of the electrons. I mean in the single half cell reaction. So on this step we need to treat these atoms with oxidation states different than 0. We need to treat as an ions. So this copper atom we treat like a copper cation with the charge +2. Charge +2 and the two electrons, every single with the charge equal to -1, give us the total charge equal to 0. +2 plus 2 minus, because we have two electrons, give us 0. On the left side we have copper atom on the in the metallic state, yes? So the copper atom with the oxidation state equal to 0. So according to the balance of the charge, the left side should be equal to the right side. And in this situation, it is correct. Let's check the reduction reaction. On the left side, the charge is, according to this atom, the charge is equal to 2 times +5, which give us +10, plus 2 electrons, so +10 plus -2 give us +8. Here on the right side we have two nitrogen atoms with the oxidation state +4. 2 times +4 give us +8. So it is correct now. Okay, so we could write now the overall reaction. Yes, so the same situation, the overall reaction, this reaction. So we are taking the substrates. Yes, we are taking the substrates which are on the left side of the arrow. So the metallic copper plus 2 atoms of nitrogen with the oxidation state equal to 5 plus, which give us copper in the with the oxidation state equal to 2 plus 2 atoms of nitrogen with the oxidation state equal to plus 4. Okay, so it's okay, we have overall reaction. However, we need to make another, how to say it, the last task. We need to fill the stoichiometric coefficients in the whole particle containing reactions here. Let's remember, let's focus on that nitrogen atom on the left side of the reaction is contained only in nitric acid. However, these atoms from nitric acid are split in the products into copper salt and nitrogen dioxide. In the copper salt, nitrogen oxidation state is equal to plus 5. So those nitrogen atoms do not change oxidation state. So they do not take a part in these two reactions. In the reduction reaction, here and here in the overall, take a part only these nitrogen atoms which appear in the nitrogen dioxide. So now what have we do? Okay, so metallic copper, we have one atom or 1 mole. So it is obvious that the salt also will be one particle or 1 mole. Yes, we have 2 atoms of nitrogen with the oxidation state equal to plus 5 and 2 atoms of the nitrogen equal to with oxidation state equal to plus 4. So we need to fulfill firstly coefficients that we are sure they are derived from the redox reaction. So we need to put 2 number. Okay, I will show you. It will be more convenient for you. Okay, here we need to put this 2 here in the front of nitrogen dioxide because we are sure that those nitrogen atoms are atoms that undergoes reduction reaction. Okay, so we can sum up the nitrogen atoms which appear on the right side of this reaction. We have 2 atoms in the dioxide. We have 2 atoms of nitrogen in 2 particles of the nitrogen dioxide, and of course we have 2 atoms of nitrogen in 1 particle of copper salt. So on the left side should appear 4 particles of, okay, I will clean it. On the left side should appear 4 particles of the nitric acid. 4 particles, but only from 2 of these particles, nitrogen atoms, undergoes reduction reaction. Okay, so we feel it, we have it. Okay, so I would like to show you now another example, another method to fulfill the same reaction coefficients. Yes, another method So